This video gives a brief insight into the formulation of a dual control strategy, which can be used for controlling unstable underactuated systems. The work proposes for a combination of model predictive control and proportional derivative control. The work does not just focus on the performance and optimality paradigms, it also explores control strategies in terms of safety. Control of real-world dynamical systems is a difficult process because of their nonlinear behavior. Several practical systems like robots, ship roll dynamics, and spacecrafts exhibit underactuation and stability issues. Low-order underactuated systems serve as benchmark as they capture all these real-world control problems. There are several traditional controller designs for controlling such systems, but they primarily rely on fixed value control strategies which do not account for system constraints and motor saturation. So using the benefits of fixed value control in tandem with predictive control is a less explored research area. Here, this work presents a real-time dual control strategy which combines the goodness of proportional derivative control and model predictive control. In the dual control structure, the outer loop is a model predictive control loop and the inner loop is a proportional derivative control loop. Talking about the outer loop, in the model predictive control loop, a control sequence based on LQ theory that is close to the optimal solution is calculated offline and used to warm start MPC. On violation of the constraints, the control law is activated in a receding horizon fashion and a control U is generated. In the case of inner loop PD, the system's arm velocity that is calculated by the outer loop MPC is provided as a reference for PD, and this inner loop PD is used to guide the system to attain steady velocity and minimize oscillations. A combination of both these controls from MPC and PD helps in trajectory tracking and stabilization. This is the proposed block diagram consisting of majorly two parts. The red box indicates MPC and MPC generates the velocity error data which is used by PD as a reference. The two control signals U of K and UP of K are combined and given to the system for stabilization and for reducing oscillation. MPC accepts information such as the output value y of k, the set point data, the cost function with constraints, and the warm start gain k. On carrying out the experiment on a 2 degrees of freedom underactuated unstable system, which is a rotary inverted pendulum in this case, the following results were obtained. It can be seen that the ISE value of MPC-PD is 1.37, lesser than that of a cold started MPC, which is 2.84. The maximum spikes in the control voltage generated by MPC-PD is 2.8, and which is lesser than the one produced in a cold started MPC, which is 4.9. The pendulum angle deviation is also minimum in MPC-PD, which is 2.2 degrees. So the overall contribution of this work is the benefit of fixed value control in tandem with predictive control is explored to develop a safe control strategy. The LQ theory based warm start in MPC provides a feasible starting point for optimization. The outer loop MPC aids in constraint based motion, and the inner loop PD provides an anti-sway action and reduces oscillation. So on concluding, the control problem involves the coordination of pendulum stabilization along with arm trajectory tracking. MPC addresses the system constraints and continuously corrects the states of the system. This work focuses on creating a control input to optimize the system's inherent dynamics, effectively utilizing the nonlinear behavior. The results obtained in this work demonstrate that the system's behavior remains bounded and converges to the desired state without causing the actuator to saturate.